So today's video is on finding all zeros, or roots, or x-intercepts. Remember, those are all interchangeable words. So today, we're going to look at different ways of breaking down our polynomials if factoring is not an option. So let's take a look at this first example. It says find all zeros of this polynomial. So we'd replace y with 0, and then we'd try to factor this out. So from our methods we learned last time, we know if we have 4 terms, we could try factoring by grouping. That's really the only method we could try. Of course, we should always be looking for a greatest common factor first, but I don't think there is any greatest common factor. So even if I tried grouping here, we did first 2 and last 2 as our groupings. Let's see, I could take an x squared out of this first pair, and that would leave me with 3x minus 5. Now remember, grouping only works if when I take out a common factor, I can make a 3x minus 5 appear from this set. And if I look at those numbers, there's nothing I can take out as a common factor that would leave me with 3x minus 5. So what that tells us is factoring by grouping is not going to work. We can't factor this through grouping. Now that doesn't mean it doesn't factor, but that means that we don't have a method to deal with it yet. Okay, so we have a new theorem called the rational root theorem. So we might need a second to pause and write this theorem down. It says for a polynomial with integer coefficients in standard form, if it does have any real, so not imaginary, real rational roots, meaning they can be written as a fraction or a whole number, positive or negative, they must be in the form of plus or minus p over q, where p represents all possible factors of the constant. So like above, this would be all possible factors of 8 over all possible factors of the leading coefficient, which would be the coefficient in front of the highest degree term. So we would do every factor of 8 plus or minus every factor of 3. Okay, and we could list out a list of possible rational roots to kind of guess and check through. And we will come back and do number 1, but let's just practice finding a list of these first. So list all possible rational roots. In other words, use our rational root theorem for this function. So let's first identify p and q. So p is all possible factors of the constant. And notice it doesn't matter if I circle the negative 12 because we're going to put plus or minus all of these factors anyway. So let's list all the factors of 12. We've got 1, 2, 3, 4, 6, and 12. That's a lot of factors. Well, luckily for us, when we go to list out q here, our leading coefficient is just 1. So all possible factors of 1 is just 1. So when we go to do our plus or minus p over q, so plus or minus, we're going to do every possible p over every possible q. So I like to write the values of p on the top, which just reminds me how to set up these fractions. So we'd have plus or minus 1 over 1, which is just 1. Plus or minus 2 over 1, which is just 2. Right? Plus or minus 3 over 1, plus or minus 4 over 1, 6 over 1, and 12 over 1. And hopefully you can see, of course, we're just going to get plus or minus all of these whole numbers. And what this gives me is a list of, well, a lot of things to guess and check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 12 possible real rational roots for this. Positive or negative 1, positive or negative 2. So if it does have any real ones, they have to be in this list. And this gives me a list I can kind of guess and check through, which is tedious, but at least it gives me somewhere to start, where otherwise I'd be stuck. Okay, so let's try one more of these. Okay, so list all possible rational roots of this function. So we've got 6. It doesn't matter if, again, if I circle the sign with it, because we're going to do plus or minus all of these. So all the factors of 6 are 1, 2, 3, and 6. And our leading coefficient this time is 3. Luckily, it's a prime number, so we don't have too many factors, 1 and 3. When we go to do our list of possible rational roots, we're going to do plus or minus 1 over 1, 2 over 1, 3 over 1. Well, you get the idea. The color changed on me. And then 6 over 1. So we're going to get a list of all of these integers. Okay. However, that is not the only possibilities. Now I need to do all of these over 3. So we'd have plus or minus 1 over 3, plus or minus 2 over 3. Now 3 over 3 reduces to 1, and we've already got 1 in our list. And remember, the only reason we're making this list is to guess and check. And there's no reason to check something twice if it didn't work the first time. So we don't want repeats. And our last one, 6 over 3, reduces to 2, which is also already in my list. So without including repeats, this would be our possible list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also 12 possible rational roots. Now they might be fractions, and those would be kind of ugly to guess and check, but if it has any real rational roots, they have to be in this list. Okay. And in fact, we'll learn later on that odd degree functions always have at least one real root. Okay, so this is the original example, the one back on the previous slide that we worked on in the beginning. Okay, so this is example 1, and we're going to go ahead and find all of our zeros. The first thing to do is list all of our possible rational roots. So let's list all the factors of our constant, 1, 2, 4, and 8. Then we want all of the factors of our leading coefficient. All the factors of 3 are just 1 and 3. So my possible rational roots are plus or minus 1 over 1, 2 over 1, 4, etc., right? So we're going to get all of our constants here, 1, 2, 4, and 8. But we also need to do 1 over 3, right? Use 3 as the denominator for all of these. So plus or minus that, plus or minus 2 over 3, plus or minus 4 over 3, and then plus or minus 8 over 3. Okay, so a really big list to guess and check through. So how do we guess and check? How do I know what's a zero of this function? We can do two things. We can test one of these zeros, like positive 1, and plug it in. In fact, remember, a very quick way to plug this in is to use synthetic substitution. So we're going to put our placeholders up here, right, as we did this before, all the way down to x to the 0. Don't forget to put in a 0 for any missing terms. And the coefficients from up here. So we have 3 for x cubed, negative 5, x squared, negative 6 for x to the first, and positive 8. Okay, so we're going to go through our synthetic algorithm. So we drop this down. 3 times the 1 in the box is 3. When I add, we get negative 2. Times negative 1 is negative 2. Adding, we get negative 8. Negative 8 times 1 is negative 8. And when I add, I get, how lucky are we? We just found a 0. Remember, if I plug this in, the last calculation is my output. I just found out if I plug positive 1 into this function, I get back 0, 1. This is one of our zeros. So we now know positive 1 is a 0. Well, how does that help us find the rest of the factors? Do we have to keep guessing and checking? I mean, we could, but that doesn't sound fun. We know if positive 1 is a 0 from our factor theorem, that x minus 1 is a factor. So if this is a factor of our polynomial, we can divide it out, right? To find our other factor, we can get a smaller factor that maybe we can break down further. Oh man, so I got to stop and do division, right? Well, let's see. So I'd need to put the, I'd put the 0 in the box, which would be positive 1. And actually, we just did division here as well, essentially, right? So where this would be my remainder. Hey, a remainder of 0. Okay, so this is my constant. This would be x to the first and the coefficient of x squared. So we now know that 3x squared minus 2x minus 8 is the other factor. So here's what we have so far. Notice we have a quadratic here that we can try to factor further. And I believe this one is factorable. Hopefully we don't have to use quadratic formula here. I'm just going to drop down my x minus 1. So let's try guessing and checking. It has to be 3x and x to get us to 3x squared. And now I need to play around with the factors of 8 that would add up to -2. Factors of -8 that would add up to -2 with our guess and check. So I'm thinking 4 and 2. Let's make -6 and positive 4x. Yep, I believe that's it. So here are all of our factors. And remember that this is really equal to 0. So if we use our 0 product property, if we set each of these factors equal to 0, we're going to get solutions from this one, the positive one we found earlier. From this one, we're going to get positive 2. And from this factor, subtract 4 and divide by 3, we end up with -4/3. So these are all of the zeros of my polynomial. Remember from the fundamental theorem that there are 3 total zeros, right? It's a third-degree polynomial, and they ended up all being real and all being rational. And check it out, they're all in my list. Positive 1 and positive 2 are in there. -4/3 would also be in there, right? If they are real and rational, they have to be in that list. Okay, here's another one. Let's try the same method. So, well, let's see. I mean, let's not automatically go here. We've got 4 terms. Is there a greatest common factor? Ooh, yes, there is. We can take a 2 out of everything. So in fact, because we're setting this equal to 0, if we factor this 2 out, we're going to get smaller numbers to deal with. -5x -6. And in fact, I can just divide both sides by 2. Divide by 2, divide by 2, and get rid of our 2. Essentially, it won't be part of the solution anymore. So to save myself some room, I'm just going to get rid of the 2. And we're going to write just x cubed. We don't need the parentheses. Plus 2x squared. Now again, if you're just asked to factor, that 2 is part of your factors, but it is not necessary to find your zeros. Right? Now, if a variable gets factored out, that's important, and that needs to stay around. But if we solve this polynomial, we should find the same zeros as the original, but now we have smaller numbers. So I've got 4 terms, maybe factoring by grouping, but if I take out an x squared here, that would leave me with x plus 2 in the parentheses, and I don't think we're going to be able to get that to match. So I don't think grouping will work this time. So it's got 4 terms, otherwise we're stuck. We need to use, our rational root theorem. So, but think about how much smaller our list is now that we've made some of these numbers smaller. Now I only need to look through all the factors of 6, 1, 2, 3, and 6, rather than 12, and all the factors of 1 instead of 1 and 2. So this is nice. So my factors of q are just 1. So our possible rational roots, we've actually made this list smaller, is plus or minus 1 over 1, 2 over 1, 3 over 1, and 6 over 1. Okay, so a little bit smaller list than we would have otherwise had. So again, that's nice for taking out greatest common factors, especially numbers that we can get rid of. So now we would basically guess and check. We'd try positive 1 in the box. Don't forget to put labels up here, so if we're missing any terms, remember to write a 0. Okay, it doesn't look like we're missing any this time, but it's a good habit to get into. Now remember, we can do this for the smaller numbers here. We don't have to go to the original, which is pretty cool. So let's even use these smaller numbers. 1, 2, -5, and -6. Okay, and then drop down our 1 and get this started. 1 times 1 is 1. When I add, I get 3. Times 1 is 3. Adding, I get -2. Times 1 is -2. And dang it, we don't get 0. So you know what that means? Try a different number. So we come back and we say, all right, let's try -1. Maybe -1 will work. So we drop down 1 again. 1 times -1 is -1. Adding, I get 1. Times -1 is -1. Adding, I get -6. Times -1 is +6. And we did it. We found one of them. We got a remainder of 0 or an output of 0, whichever way you want to think about that. I now know -1 is a 0 of our function. So we found one of them. Remember, our fundamental theorem here says that there are 3 total, real or imaginary. We found one. So -1 is 0, which means x plus 1 is a factor. And again, we would divide that out, but essentially we already have, right? This is the 0 of my divisor. We've done the division synthetically. We just need to interpret our answer again. So this would be the constant, the coefficient of x to the first, and x squared. And our other factor, so here's the x plus 1 we just found. Our other factor would be x squared plus x minus 6. And of course, this is still equal to 0. And we would try to factor this out. The factors of 6 that subtract to 1 are 3 and 2. They're opposite signs. I think plus 3 and minus 2. A little bit easier to factor this time. And there we go. Setting each of these equal to 0, we get -1 from this factor, -3, and +2. And all 3 of ours were real, they were rational, and they were even in my succinct or shorter list. Okay, our last one here is just kind of an application. Find the expression for the missing dimension if the volume of this figure is given by this polynomial. Well, to find the volume, if you remember from geometry, kind of do length times width times height. So volume is length times width times height. You multiply these 3 dimensions for rectangular prisms. So and that's just a cursive L. So we know a couple of these. I know what my volume is. It's the x cubed plus 9x squared, etc. plus 20x plus 12 equals the length, which is x plus 6, times our unknown width. We'll just skip that for now, because remember, when you multiply these, the order doesn't really matter. So let's put our height in, and then we'll say our unknown width. Right? We just say w is our unknown. Well, if I'm trying to solve for w and these 2 things are being multiplied by it, we would need to divide by x plus 6 and x plus 2. So there's 2 ways of doing this. You could multiply x plus 6 and x plus 2 together, get the quadratic, and then do long division, because you'd have to use long division if your divisor is a quadratic. Or, probably the better method here, both of these factors I can do synthetic with. So I could also do synthetic division twice. So that's my preferred method. I would put the -6 in the box. My coefficients are x cubed, x squared, x to the first, and x to the 0, or a constant. And our coefficients are 1, 9, 20, and 12, all positive. Not very straight there. Okay, so let's go through this. Drop down our 1 times -6, adding we get 3 times -6, adding we get 2 times -6, and beautiful, yep, it went in there. So we got a nice remainder of 0, and it tells me this is my remaining constant, this is x to the first, and this is x squared. Now remember, we divided out x plus 6, let's just divide out the x plus 2 from what's remaining. So that means we would put -2, the 0 of our divisor, in the box. And we only need to divide it out of what's remaining here, right, to find our final piece. So my coefficients are 1 for x squared, 3 for x to the first, and 2 for x to the 0, or my constant. So we're essentially just taking our already broken down factor and breaking it down by the last one. Okay, so again, we'll go through our algorithm, drop down 1, color didn't change on me. Sorry, drop down 1 times -2, adding we get 1 times -2. Beautiful. Another remainder of 0. And this would be my constant, or the constant, and this is the coefficient of x to the first. So it looks like x plus 1 is our remaining factor. So the missing dimension over here should be x plus 1. Okay, again, you could have gotten this by doing what I did, which was synthetic division. Hopefully you get a remainder of 0, because that should be a factor. And then use synthetic division again, but of your answer, right? Or you can multiply these 2 together, get a quadratic and do one long division. Either way, you should end up with x plus 1 is your missing dimension.